Hi, this is Mr. Royks, and what we're going to do today is this podcast will be dealing with equilibrium constant, which we abbreviate as KEQ. So, equilibrium, as we mentioned before, is when the rate of the forward reaction and the rate of the reverse reaction are equal. Well, equilibrium constant takes into account the actual concentrations of the products and reactants. So each particular reaction has its own equilibrium constant. And the value of the equilibrium constant can be found by taking the ratio of products to reactants at equilibrium. So, for example, again, the formula for KEQ is KEQ is equal to the concentration of products over the concentration of reactants. So that's how we would solve for KEQ. And as I mentioned earlier, that each equation is going to have its own equilibrium constant. Now remember that the equilibrium is not when the reaction stops, but it is just when the forward and reverse reaction rates are equal. Some of the things that we can learn from the equilibrium constant, the KEQ, is, in a reaction, whether there are more products or reactants at equilibrium. So think of this: if there was an equal number of products or reactions, equal concentrations of products or reactions, say there is 2 molar of products, and the concentrations of reactants was also 2 molar, think about what your KEQ would be. Your KEQ would just be a value of 1, equal parts. So whenever KEQ is 1, that means you have the equal value of products and reactants. Now, other reactions have much different KEQs. So say we have a KEQ that is equal to 3.3 times 10 to the negative fifth. So what would we be able to tell from that reaction? Well, think about it. We know that if the products and reactants are 1, then they're equal. If we have a value, obviously this value is much, much smaller than 1, right? That would result, or that would be coming from a reaction that is heavily favored on the reactant side. It means we have a small number of products, but we have a large number of reactants. That would get us a small KEQ. Now, if we look at a KEQ, say we're given a different KEQ, and the KEQ is given to us is 5.2 times 10 to the second, okay, what can we tell from that? Well, compare it to our value of KEQ when we're in equal proportion, right? We have a 1. So that would mean that if we have a large number here, that means that particular reaction highly favors the products. And so we would have a lot more products and we'd have a lot less reactants. So those are a couple things we can tell from KEQ. One of the things about KEQ is it has to be determined by a laboratory procedure or lab data. We can't look at a reaction and come up with a KEQ value. We have to be either given the KEQ value, and if we are given the KEQ value, that is based on laboratory data, or we could be given the data from a lab and being able to solve for KEQ. My final piece of information to you on this particular subject is when we look at a reaction that hasn't reached equilibrium. When we have a reaction that hasn't reached equilibrium, what we look at, instead of the KEQ value dealing with the concentration of products or reactants, we would take the concentration of products over the concentration of reactants, and that is called the Q value. And Q stands for reaction quotient. See if I have enough room there. Reaction quotient. I may have spelled that wrong, but what that is that's like a snapshot of a reaction. The reaction hasn't yet reached equilibrium, so it's not a KEQ value, but the reaction quotient is, again, what the relationship between products and reactants is in a given reaction at a certain time. Now, what happens when Q is equal to KEQ? When we have a Q equal to KEQ, we are at equilibrium. So Q is equal to KEQ at equilibrium. And I think that's about all the information for today. What you should now go to the web and find some information, do some research, find some information that will work in trying to teach this topic in a different manner. All right, and we'll see you in class.